In this video, we'll talk about one more term from linear algebra. It's going to be super important as we work forward to connect all these topics together and to be able to solve our important problems later on, and that's the idea of the rank of a matrix. So the rank of a matrix is defined to be the number of linearly independent rows of the matrix. We're talking about columns before, and we'll get to that in a moment, but we're thinking now about linearly independent rows of the matrix. How can we go about determining this? Well, we already know how to count the number of linearly independent vectors in a set. We put them all into a matrix and we row reduce that matrix. However, that method we've done previously involved putting the vectors that we cared about as the columns of the matrix and not as the rows. So you could write a new matrix that has the original rows as columns and do the same process. That's called taking the transpose to get that new matrix, and then do row reduction. Or you could actually take the matrix you start with and just row reduce it. The idea here is that all of our elementary row operations are linear combinations. So we're not really doing anything illegal here by doing row operations. And the process of row reduction, its goal is to make as many things zero as possible. So by making as many things zero as possible, you're really funneling down to which ones are important, which ones are linearly independent. So in that case, we could also get this rank, or figure out how many linearly independent rows there are, just taking our matrix at the beginning and row reducing it. So to tie this bit together, we need two more definitions, and that's that of the row space and the column space. So let A be a matrix. This could be a non-square matrix if we wanted, so A could be m by n. It has m rows and n columns. So the row space of A is the span of the rows of A. So take the rows of A, those are all vectors, and we'll take the span of them, that gets me what's called the row space. Now the rows here, since there are m rows and n columns, every row has n entries in it, so these will be vectors in Rn. We can talk about the column space in the same way. It's the span of the columns of A. So now you're taking the columns as vectors and taking their span to get the column space. Now, since this is an m by n matrix with m rows, these are all vectors in Rm. So with these ideas, we can define the rank in another way, which is going to allow us easier access to how to compute it. So the rank of A, usually written rank of A, is the dimension of the row space. We take those vectors, figure out linearly independent. The number of linearly independent vectors is the rank, which is what we want. However, this is also the dimension of the column space. Why does that work? Why are they the same thing? Well, let's think about how we would determine these different dimensions. So if we're looking for the number of linearly independent rows, we're going to take A as it is and row reduce it. And let's say we're left with a matrix that looks like this once we do that. There's our matrix. Now, how do we count the number of linearly independent rows? Well, we've done our reduction. We've thrown out all the unimportant stuff. So the number of linearly independent rows is the number of non-zero rows in the row echelon form. In this case, we would get 3 from 1, 2, and 3. The bottom row is all 0, so it does not count. Now, what do we know about each of these rows? Well, because we're in row echelon form, each of these non-zero rows must be headed by a pivot 1. So we have 3 pivot 1s here. But we're talking about using columns to find linear independence. We had exactly the fact that the number of pivot columns was the number of linearly independent columns. But since every non-zero row in the echelon form has a single pivot 1 in the front of it, the number of non-zero rows must be the same as the number of pivot columns. So since every non-zero row in the echelon form starts with a pivot 1, and that's the only way to get any pivot 1s, we know these two things must be equivalent. So we can find the rank just by taking the matrix and row reducing it, and then counting how many pivot columns we have. That will give us the same value as number of independent rows, and any other way we would want to compute it. So Rank of A is number of pivot elements in the row echelon form of A. We'll see this rank come up a little bit later. We're talking about things like determinants and how it relates to those. But this gives you the idea of what that rank is and how to compute it for a given matrix.